Hey y'all, I'm Sunny Shell, and tonight I'll be discussing the Big Bang with Dr. Damian Christian. So sit back, buckle up, and let's get to the sunny spot on Skeptic Haven.
Jefferson laid great stress on it. It wasn't enough, he said, to enshrine some rights in a Constitution or a Bill of Rights. The people had to be educated, and they had to practice their skepticism and their education. Otherwise, we don't run the government. The government runs us.
Hey everyone, thank you so much for joining us on this Thursday evening. I want to thank Dr. Damian Christian for joining me tonight. Thank you so much.
Thank you for having me. It's a pleasure to be here.
Absolutely. And we have some great topics tonight. We're talking about the Big Bang. And first of all, is the Big Bang the best model for how our universe started?
Yeah, there's lots of evidence for the Big Bang. There's 99 out of 100 cosmologists, people who study the origin and evolution of the universe. Not the people who cut your hair; they're cosmetologists, but cosmologists. Most accept the fact that the universe formed about 13.7 billion years ago in an infinitely dense, infinitely small speck that was the Big Bang, and then it's been expanding ever since. And there's the Fred Hoyle never accepted the Big Bang going back into the 1950s. He believed in the steady state model and that some of the parameters we measure were fake. And he's sort of in the minority. The fact that the universe is infinitely old and static, and you have to explain away a lot of Big Bang evidence to sort of have that theory, but that's called the steady state theory. And that's really the only alternative I know of to the Big Bang. Reese at Cambridge, I think he has this idea that we're just one of millions of universes, and we live in the universe where all the parameters come together that we can have life and stick together and have gravity and light and things. So there may be millions of empty universes out there, but I think that's really hard to prove, and it's kind of over my head. It's too hand waving. You get into lots of good discussions, but you can't really get to the bottom of it. But yeah, so the Big Bang is our best theory, and there's probably 5 really good pieces of evidence. We have the redshifts of galaxies showing that the universe is expanding. We have the leftover glow of the Big Bang called the cosmic microwave background. We have the origins of light elements, the fact that stars have cooked up most of the heavy elements in the universe, and that the universe formed mostly with hydrogen and helium and a little bit of lithium. And then there's also the fact that the universe is so homogeneous. It's sort of the same everywhere, and that it looks the same everywhere. As astronomers, we have to hope our observations are telling us the truth. And now that we have the James Webb Space Telescope, it's pretty amazing because we're seeing the building blocks of galaxies, and nobody really. There's lots of in the press people are saying, "Oh, it's a big surprise," but we've never looked this far before. We've never looked back to the early, few hundred million years after the Big Bang. So a lot of these discoveries are exciting. So maybe there's 4 main pieces: the redshifts, the cosmic microwave background, the origin of light elements, and then of course the fact that the universe is so homogeneous. So
Awesome. So, for those of you who are joining, we want to thank you so much. This is going to be a great discussion. Those of you who are regulars to my channel, they know that I really love these type of topics. Anything that has to do with space and black holes and the Big Bang, and that's really what I love to talk about and learn about. So I wanted to start with that, but before we go too farther, I wanted to ask you, can you, you've been on the show before, but for those who don't remember you, can you give just a little bit of a background on yourself and who you are and how you ended up on my show?
so thanks, Sunny. Yeah, so I'm Damian J. Christian, and I'm a 16th year as a full professor at California State University, Northridge, outside of Los Angeles. And through our good friend who works on black holes, Dr. David Garofalo, I was introduced to Sunny on the show, and I did my thesis on neutron stars and black holes that emit X-rays and that were actually observed with the Einstein Observatory in the 1980s. But so, and then David I have a few papers with David trying to look at black hole jets and their different properties, and David has a model for accretion. And so, but mostly I've been working on the sun lately, and the sun's been interesting. It's had two big X-class flares yesterday that caused some radio blackouts. And so we should do a show on the sun later on. But so right now, the last 15 years, I've been mostly focused on stellar activity in our sun and solar flares. And I got my PhD in 1993 at the University of Maryland. Go Terps.
Okay. Awesome. Well, yeah, we have a lot of things we could talk about. As you were talking, I was remembering, it was like things are popping into my brain about that show, and I was almost giddy excited with the discussion that we were having. So, yeah, thank you so much for coming back on. I really do appreciate it. So you mentioned cosmic microwave background radiation. And I hear a little bit about that here and there. And so for our audience, can you kind of talk about what that is and why is it important it's kind of one of the foundational pieces of evidence for the Big Bang cosmology.
Yeah,
so could you talk a little bit about that?
Yeah, so the idea is that the universe, this is what's always confusing, it's not really expanding into anything. The whole universe is just expanding. And maybe after about 400,000 years, it started to cool. For the first, few 100,000 years, it's too hot for atoms to even form. So you have, electrons and protons not combining. And so then at some point, the universe cooled enough to be transparent to radiation. And then you can think of it as being stretched, like you're stretching a balloon. And so that 3,000 degree gas from 13.3 billion years ago is now cooled down to about 3 degrees Kelvin. And what was his name at Princeton? I forgot his name. Yes, Robert Dickey at Princeton was working on this idea that you should be able to detect this. And Penzias and Wilson were at AT&T Bell Labs, and they were trying to do some other observations of supernova remnants. And they kept seeing all this static no matter where they pointed their horn antenna. And Penzias, they got the Nobel Prize for the cosmic microwave background in 1978. And Penzias just passed away about 2 weeks ago. I think he was 90 or so. But they made this serendipitous discovery. The antenna was full of pigeon crap, so they had it cleaned, thinking it would get rid of the noise. And after that, it still had all this static, and anywhere they looked. And so in talking to the people at Princeton, they realized, hey, we've discovered this prediction about the Big Bang, that there should be this leftover afterglow. And they measured about 3.5 Kelvin. Subsequent measurements got it down to about 2.7, which agrees with the expanding and cooling in the Big Bang. And of course, the clumpiness of the cosmic microwave background might tell you something about how galaxies formed. If there's big spots in the cosmic microwave background, like big clumps, it might indicate that there was lots of mass in the early universe making big galaxies or big structures. And if it's not so clumpy, then maybe the universe is empty. And until we discovered dark energy in the late 90s, we sort of thought the universe was mostly empty. It was only, 20%, or now it's 4% real matter, 26% dark matter, and 70% dark energy, which doesn't give you a warm, fuzzy feeling. But, the cosmic microwave background, not only can you sort of say this is a good piece for the Big Bang, you can try to measure its clumpiness. And they do, I can have a slide later, but they try to do these autocorrelation functions to look at the structure. And now it looks like the universe wasn't really super clumpy and it wasn't super empty. It was kind of in between. And so this supports kind of a universe that will expand forever, just like a rocket that just has enough energy to leave the Earth. One that it's too slow to fall back. I mean, if the universe were super massive, it might have stopped expanding and collapsed, and then we wouldn't be here, right? So it had to just exactly have enough energy to sort of keep expanding, and it may expand forever. It may not. We'll talk about that later. But the fate of the universe is a fun topic. So.
Well, that kind of goes right in. We are already getting some great questions from our live chat, and what you just said just kind of went perfectly with Carrie Ann Chrysler's. Is there any reason to think that Big Bangs are one-time events or could be a part of a long cycle. So Big Bangs is in plural. That's kind of an interesting
Yeah, no,
concept. And we talked
that's
a
a
little
great
bit about that behind the
yeah, that's
scenes.
a great question. Thank you, Carrie. And yeah, so it could be that every 20 billion years or so, maybe the universe stops expanding, collapses, and then we have a new Big Bang. And some people sort of like this idea because it says that even if we screw up this universe, we'll get a new one later on. But I mean, I don't know if there's a lot of observational evidence for that. It sort of goes into what Martin Rees has with his multiverse. If there's other universes alongside of us, I don't know how we'll detect them. I mean, there's some papers I've seen recently I didn't read, of course, about somehow with the event horizons on black holes may tell us if there are other universes or something. But I think some people really like this idea that we're just one universe in a series of cyclic universes. But I don't know if that I personally don't know of much evidence that supports that, other than it's sort of a nice theory. It makes you feel good. So
Well, I kind of wonder along that line if, when you said that if we didn't have enough energy, it might have collapsed down. You kind of have to have the right amount of energy. I
right.
wonder if it's possible that maybe in that cyclical way that she was talking about, maybe there's only one, but it has contracted, gone back and forth, and ours is the first one or the second one, who knows, that has had life.
Yeah,
You
yeah,
know,
exactly. Yeah, I mean, it could be we could have had a few duds, and then finally you get this one that's has enough elements and all the right parameters for gravity. There's sort of the six magic parameters: the strength of gravity, the strength of the strong nuclear force, weak nuclear force, electromagnetism. And if those numbers are different by some tiny amount, then the universe wouldn't exist as we know it. So
awesome. So
maybe
I'm
that's
gonna,
a little better than the multiverse, because this way it's multiple verse universes, but in time.
right. I
Marianne should
kind of like that
publish
one.
that theory and call it her theory. Yeah.
I'm sorry. Here, who you said had
The person
published
asked
that?
the question, she can claim this as her theory, that they're
Oh,
multiverses, but in time.
there you go. Awesome. So, Carrie, you now have a. And I'll do one more, and then we'll catch the rest of them in just a minute. But this one kind of segued in essence. What are the effects of the continual stretching of our universe? So that's a great question from Toy Soldier 727, because it also, piggybacking on that, we know that we're also expanding faster. And so, does that have an effect itself? So, great question, Toy Soldier.
Yeah, thanks. Yeah, I mean, we think of the universe as kind of like if you taped a bunch of coins to a balloon, the coins aren't expanding, but the balloon is. And so, there's some worry that dark energy will keep getting more energetic, and will sort of lead us to a big rip where the universe just kind of becomes so vast, and everything is remote and just kind of fades away. Or if it stops expanding, then they call that the big crunch, that maybe we'd fall back in and have another big bang possibly. But I mean, I just think it makes it seem a little desolate that if we're continually stretching, space time. It's sort of a hard concept to picture, because the first question you want to ask is, well, what's outside the universe? But there's nothing outside of it. It's everything. And I remember when I was at Penn State as an undergrad, I asked the professor, well, where's the Big Bang? And his answer was, it's everywhere. You can think of it as sort of a point that's being stretched in all directions, and whatever geometry it has, it does. And if it continually stretches, I think we'll just kind of fade away. Good old
Hmm.
Blondie, right? But
Yes, absolutely. I've also, with you saying that about there is nothing outside of our universe. It also kind of makes me wonder if, I mean, there's no way for us to be able. We don't have the technology anyway right now, and we may never have the technology to be able to see beyond or to know what happened before or any of those type of things. But I do wonder, and maybe it's my own security blanket, come to think of it, that there is something, and that this is just our, all that we know. It's like if you're in a room and there's a whole house, but all you see is that room. You would never get out of that room in your whole life. You may think that that's all that there is, You know what I'm saying? And that might
Right.
be a security blanket kind of a thought too.
Yeah, I think we've, historically, I think even cosmologists have sort of wanted a comfortable universe, right? When I was in graduate school,
Yeah.
everyone thought there should be enough matter, this parameter of sort of the real density of the universe or the critical density compared to the real density should be about 1. But there's no reason it should be, right? Now it looks like it's the true matter that we see in stars and our favorite planets and things is really is only 4% of the total. But I mean, one of the interesting things, like I was mentioning, I'm not that familiar with it, but there are people who think that how black holes interact with the event horizon and sort of the curvature of space time may give us some clues if there's a universe next door. I saw a brief headline. I didn't read the paper, so but it is interesting that there may be some clues that there's a room next door, but I'm not familiar with those. So
Yeah, that's the
maybe
thing I love
maybe
about
David
black
said he's
holes.
going to tune in. We'll ask David.
Okay, that sounds good. It's so fast. Black holes just fascinate me.
Yeah.
I think because of the promise, they're scary, but they're also so much promise. Like, are they um, places where the space time kind of folds so that you can end up having, you know, travel from one place
Yeah.
to
A
another? If you can ever
wormhole. Yeah.
figure out how to not stretch yourself into oblivion, but
Right. Yeah. Yeah. Well, there is a certain as you get a more and more massive black hole, the event horizon is bigger and bigger, right? So there might be a supermassive black hole where you could get through the event horizon. The tidal forces are a bit more spread out.
yeah, there you go. I'm going to hold
Yeah.
on hope for that.
Yes.
All right, so I'll get back to the rest of the audience or live chat questions shortly, but I wanted to have us continue on. We've talked about um, background, cosmic microwave background radiation, and we talked actually a little bit about dark matter. And but can you tell me a little bit more about the role that dark matter kind of plays in the universe? Dark matter, dark energy, and I'm fascinated that there's such a high percentage of the universe that is both of those.
Right. Yeah, well, one of the things that we don't really know what either dark energy or dark matter is, but dark matter is it's sort of back in the 1980s and so on when Vera Rubin discovered uh, this extra component. We thought most of the mass in the Milky Way would be in normal stars, luminous matter stars and planets and things. But then she found about 80% of the Milky Way was in something that wasn't making light. So it got nicknamed dark matter. And it causes stars that are far from the center of the galaxy to still have really high velocity. So we measured a dynamical mass for the Milky Way and other galaxies. And that shows us that at the time, we thought of the universe as being 20% regular matter and then 80% this dark matter. And then, of course, in the late 1990s, when we thought the universe, we would go out and measure the slowing down of the Big Bang and kind of the standard, what they call the cold dark matter universe. Adam Rees and others, Schmidt, and they got a Nobel Prize for the accelerating universe, which was completely, no one expected that. They sort of expected to go out and measure the slowing down of the universe. I was at a meeting in Fermilab for the Sloan Digital Sky Survey, and they were like, "Oh, cosmology solved. We should go do something else because the universe is the cold dark matter is fits pretty well." And then, of course, they discovered the universe actually accelerating, and then the model for that acceleration is there's some type of vacuum energy that's giving like a Red Bull at 2 a.m. to the universe, and the universe is speeding up. And dark matter, Ed Wooten joked that it was the most embarrassing observation in physics.
Oh,
But
really?
yeah, because we don't really. I mean, it's sort of a, we see the universe now. These distant galaxies that we measured with exploding white dwarfs called Type 1a supernova, they're actually 25% further than they're supposed to be, which means they moved away faster. And then, in the early 2000s, this accelerating universe was quite controversial. People said there must be some error in the measurements. There must be extra dust in these supernova, and then so the three different groups kind of all got the same answer that the universe is actually accelerating. And now that we have James Webb, we'll probably find even more distant supernova to sort of, and it looks like the acceleration isn't constant, right? This epoch we're in now seems like it's bigger, and then it may have been slower earlier. And so then this as we talked about, what's the fate of the universe? How is the expansion the stretching gonna affect us? Well, it may speed up, and then we'll even find the big sort of rip even quicker, right? So,
Mhm.
but dark energy, I always think of as just kind of like this name for our ignorance of what the universe is accelerating, and they've done experiments where you can have particle antiparticle pairs come out of nowhere and annihilate and give energy to the universe. That's sort of the quintessence, they call that. That's sort of one idea. And they've done this in the laboratory going back to the 1940s, where you bring two electric plates together and you can sort of force particle antiparticle pairs to come into existence and annihilate. I think it's called the Casimir effect. But we really don't know. I think this is one of the next big missions for NASA, is to have uh, an imager that will look for distant type 1a supernova, like be dedicated to them. We only have about one supernova per galaxy per century, so you need to look at lots and lots of galaxies. And then the WFIRST, I think it's been renamed the Nancy Romaine Space Telescope, and hopefully, be launched probably in the next few years, and it'll be dedicated to looking for these distant supernova to use as cosmological indicators. And so that's the next great, after James Webb, that's probably one of the next great missions that NASA will have. And so as we made the measurements over and over again in the 2010s, turns out that normal matter is 4% of the universe, dark matter is about 26%, and dark energy is about 70%. And of course, dark energy is the most unknown, and it's like those Calvin and Hobbes cartoons where he's eating a chocolate chip cookie and he says the universe is too vast to figure out, but I'm sure we'll figure out. I always tell my students it's job security trying to figure out what dark energy is. So
Absolutely. I wonder if we will ever have the technology to be able to learn what it is. I mean, I hope so. It's just so it's so mysterious, I guess.
right.
It just seems like such a mystery. So I'm going to go back to another question from our chat, and this is another one from Carrie Ann Chrysler. The detectable energy is expanding, so we are detecting the surface tension of the bubble, and that within the bubble is the universe.
Well, we're not really seeing the bubble. It's sort of like, being in the forest, we can't sort of see the end of the forest. So I mean, in a big picture, you might think of it as a giant bubble, but I mean, we're seeing galaxies move away from each other, and we're seeing this acceleration that further galaxies are moving away faster. But I'm not really sure we're sort of, if you think of it as a bubble, we're not really seeing the bubble. I don't think we're sort of just measuring pieces of it. It's sort of too big and too vast, and it's weird because there's sort of no center and no edge in the Big Bang, right? It's sort of everywhere. It's like this point that's been stretched. But I had the same question as a young person: is where's the Big Bang? And of course, it's everywhere. And I think it's easier in our brains to picture it as a sphere, but it could have sort of any geometry. But there's nothing outside of it because it's the whole universe, which is, I think, a hard concept. So, but that's a great question. We
Absolutely.
think of it. I think the bubble is a little bit hidden. It's sort of like the Wizard of Oz behind the curtain. We just sort of measure these pieces in terms of redshifted galaxies and the cosmic microwave background, and the other pieces with the abundance of light elements, and try to put all those together. So.
Yeah, I think that it's very difficult for well, at least for my brain, to try to conceptualize what when the Big Bang is everywhere. Trying to conceptualize that is so difficult because we think of things as having points in space or
Yeah,
points in time, and
yeah,
so I think that's what makes it so difficult to try to grasp.
yeah. The textbooks like to show the example of an ant on the surface of an orange, and he's going to run around and think that there's no edge to this
Yeah.
orange. He's on the surface, so he's living in sort of 2D, but in the 3D, he's sort of running around the top of a sphere. And so there's ideas that in the future we can try to, the fate of the universe is determined by how much stuff is in it, how much mass. And if there's lots of mass, it'll stop the expansion and it'll have the big crunch. It'll collapse. And so that's kind of a spherical geometry. But if it's going to expand forever, it might have kind of a saddle shaped geometry. And so
Mm.
if you had 3 space lasers making a triangle, over say millions of light years, you could try to measure the geometry of the universe. This has been an idea from years ago that I think they, with LISA and things, the gravitational waves is a new piece that allows us to sort of peer through some of this gas and dust, that we can maybe get more constraints on dark matter and dark energy by having gravitational wave measurements of distant galaxies. And so that's kind of I had a slide. I didn't have it in my slide deck, but I saw a slide once that said, gravitational waves let us peer through the curtain to see even more distant things in the early universe. But it's not so easy, because you need a sort of 2 merging black holes to make a big signal, to make a gravitational wave. And so something in the early universe that's kind of in the noise, we may not be able to detect very easily. But I'm sure there's probably plans. LISA, it was the space mission, and LIGO has been running out of Louisiana for a few years now and had some amazing results. They're measuring the change in the length of their interferometer to 1 part in 10 to the 20. So 1
Wow.
part in 1 with the 20 zeros after it. So it's really an incredible tiny, this 2 black holes merge and they sort of cause a ring in space time. So that's a whole other. You should probably get a gravitational wave expert for that. But it is exciting that some of these unknowns that we have about, what's the distribution of dark matter, what's going to happen with dark energy, gravitational waves may help us sort of narrow that down.
So the next one is from Wes, I'm sure. Open, closed, or flat universe, and how do we know? You kind of a little bit of touched on that, but
yeah, no, that's a great question. I mean, if it's like a rocket leaving the Earth. If it doesn't have enough velocity or energy, it's going to fall back, and we think of that as kind of being a closed universe, and then that would have sort of a spherical geometry. And if you think about the universe being really empty, and then it's going to kind of expand forever like a super fast rocket, it has a low density, then we think of that as being an open universe. And in an open universe, it's going to have kind of a saddle geometry where a triangle would have less than 180 degrees because you're kind of saddle shaped. And then flat, the universe is expanding exactly at sort of it has exactly the density and mass to where it's just going to kind of expand forever, just at that limit. It's not open or closed. And it seems like the clumpiness of the cosmic microwave background sort of indicates that we're living in an accelerating, expanding flat universe. And so,
wow.
But there's still, when I was in graduate school, I think, and it was getting back to the cyclic universes, people wanted there to be enough matter to close the universe and sort of have it fall back on itself in kind of a closed, and maybe it happens over again. But then it looked like, in the late 20th century, we didn't really have enough mass that it was open, that was going to just kind of fly apart in sort of the big rip. And then now that we have the big component of dark energy and dark matter, and that they've measured in the clumpiness of the cosmic microwave background, it looks like the geometry might be flat, and so it's going to expand just forever. So,
great question, Wes.
Yeah.
Great question. That's just fascinating to me. So, you had talked about the James Webb telescope. Has that completely thrown things kind of on its head or changed the way we think about things, or has it maybe given us some surprises, but it's not, we talked backstage about how the media tends to make it seem like it's, oh, now, everyone is questioning everything they ever knew, but maybe not actually. So I'm just curious, how has that changed our thinking?
Yeah, I think that there's a lot of great discoveries, and that we're still sort of sorting through it. I don't think it hasn't disproved, there's something called the Hubble tension, where now the measurements with the expanding universe, that Hubble's constant, the rate the Hubble's constant is a weird number. It's a velocity per distance, so it really has units of 1 over time. It's measured in kilometers per second per millions of parsecs, and a parsec is just about 3.3 light years. So it's just a unit of measurement. And so right now, the galaxy expansion is showing us a Hubble constant of about 73, whereas the cosmic microwave background, the newest measurements show that it's about 67. And 10, 15 years ago, the error bars used to overlap, and people were like, oh, this is okay. But now people are saying that the error bars are tiny, and there's a true difference in the two measurements, but it could just be in the measurements, and maybe James Webb will help for the really distant uh, galaxies and supernova that we measure. But I don't think it's, I think it's still the third quarter for the, James Webb is done. It's seeing things that are really a surprise about these different weird little galaxies in the early universe. Supermassive black holes in the early universe, they shouldn't have had time to form, but it seems like we have a handful of billion solar mass black holes that are less than a billion years old, and some of these galaxies seem to have formed too quickly. But the truth is, we've never observed this before, so we didn't really. It's like trying to guess what's up ahead. We didn't really know what happened in the first kind of billion years, and now that we're observing it with James Webb, I just think it's not going to. I think the Big Bang is going to stand the test of time, but we're still going to have to work out, some of these pieces. And the Big Bang has, as we will talk about later, maybe there's one big kludge in the Big Bang. Because the universe is so isotropic and homogeneous, if any of the expansion in the early universe was off by 1 part in 10 to the 55, the universe wouldn't exist. And so it takes an incredible amount of fine tuning to get the Big Bang to work. And the way they did, the way they froze in the isotropicness was to have inflation, where one time only do we violate the speed of light, and the universe is allowed to go from the size of a proton to the size of a beach ball instantly. And that way, all the structure is frozen in. The fact that it has the same clumpiness in all directions, and the inflation has been accepted. Lind and those guys, and Guth, I think they got big prizes for inflation, but it just seems such a kludge that and it may have to do with when the different forces separated in the early universe. You can think of, the Big Bang. After the Big Bang, the universe was trillions and trillions of degrees hot, right? So there was no matter yet. You didn't have protons or electrons yet, and then as it cooled and formed protons and hydrogen and helium and maybe a little bit of lithium. And then the forces early on separated, the strong nuclear force. When the guts force is separated from gravity, maybe that's when we get this big expansion. But I think that was kind of an afterthought. Cosmologists are probably yelling at me now that I'm misrepresenting.
Well, you bring up a really great thought. It's almost like moving backwards a little bit in the discussion, in a sense.
Yeah.
Because there's so many people who think of the Big Bang as a big explosion. But I wonder if if a better term would be the Great Expansion instead of the Big Bang. And how exactly does that? Wasn't there something that created the Great Expansion, or the?
Yeah, there had to be a singularity, and we don't know where that singularity came from, and it's sort of, it's hard to wrap your head around the fact that if it came from nothing, if it was just a fluctuation but it's sort of like a black hole singularity, infinitely dense and infinitely small, and then 13.7 billion years ago, it created the universe, and then I forget the exact time, but within some fraction of a second, we do inflation where it goes from the size of a proton to the size of a beach ball. We violate special relativity one time only. Well, it's the only time we're allowed to do it. And then that freezes in the structure, and then it expands, for the next 13.7 billion years. And of course, there's no, the universe is radiation dominated for about the first 400,000 years. And then as protons and capture their electrons, and you get to have atoms, and the universe becomes transparent to radiation, then that's what we see when we see the cosmic microwave background. And when that happened, the temperature of the plasma or the gas in the early universe was about 3,000 degrees. And then if you stretch that over the time of the universe, then we expect it to be about 3 degrees Kelvin, which is really a very, really low temperature, right? Absolute zero is the smallest. And so 3 Kelvin is our, uh, was sort of predicted for the Big Bang model, and it agrees with, with what Penzias and Wilson serendipitously discovered in 1965. And that's, so that cosmic microwave background and the fact that Hubble saw all these galaxies moving away was really some big surprises. Hubble's discovery of the expanding universe is been called the biggest discovery of the 20th century. And I would think dark energy is the biggest discovery of the 21st energy. The fact that in the simple Big Bang model, it should be slowing down. On the 18, when Mr. T gets blown up in the air, he falls back, right? The
Yeah.
universe should be losing energy, not gaining energy. But now we kick in this component that we call dark energy, and the universe is actually accelerating. And then I don't know if it seems like right now the acceleration is the biggest, and maybe dark energy is sort of increasing with time, but I don't think it's well known. I think that's why we're going to have the next, Nancy Grace Romaine Space Telescope to try to measure more distant supernova, because James Webb could probably do it, but it would use up, it's a big fancy telescope. It can look at exoplanet atmospheres. It has lots of other things it needs to do, so it can't be chasing after all these supernova. And so the more type 1a supernova, which is our favorite super far distance indicator now, because when a white dwarf explodes, a massive white dwarf, we think that happens with the same energy anywhere in the universe, so it's going to happen with the same brightness. So if we measure the brightness, we know how truly bright it was. Like knowing that light down the hallway is 100 watts, you can tell how far away you are. If you didn't know the wattage, then you wouldn't know the distance. So cosmologists love type 1a supernova. That was sort of the key to finding dark energy. And then, of course, Schmidt and Perlmutter, and yeah.
So, with all of that, is that what I've heard the term stellar evolution?
Yeah.
Are we this whole conversation discussing stellar evolution, or
no, not really?
We're
sort of talking about the racetrack, and then the stellar evolution are all the cars, right? So, stellar evolution is super important because, well, one, the brightest and biggest stars are going to help us see the furthest, right? So that there's kind of cosmologists always talk about a distance ladder, which you have to calibrate. And Hubble actually got a terrible value for the age of the universe because his distance ladder wasn't correct yet. You have certain pulsating stars, and if they're large red giants, they pulsate slowly. They're about 10,000 times brighter than our sun. If they pulsate very quickly, something called Cepheids, if they have sort of a 1 to 3 day pulsation period, then they're only going to be about 10 to 100 times brighter than the sun. And so Henrietta Leavitt and others, they made this period luminosity relationship. And so if you measure the period, the true brightness of the star. And those stars only pulsate after they've aged and started to become red giants. So that's a really key piece. And the Hubble Space Telescope, in my opinion, is kind of called the Hubble Space Telescope because its key project, and I have a slide, it was to measure the distances to Cepheids to sort of calibrate Hubble's constant, right? So,
do you want me to bring that in and let you find that?
Real quick. Let me see what slide am I thinking of? Let's see. Yeah, so that's the Big Bang. But yeah, so here, this is Wendy Freeman's paper from 2001, where they used all of these sort of special types of pulsating stars called Cepheids and RR Lyra stars. Sorry, it's the RR Lyras that have the short periods. Cepheids can have long periods. But so this was the key for the Hubble Space Telescope, the fact that this is as we make the distance ladder, sort of the middle rungs are going to be these pulsating stars. And so this is the first sort of standard method then is to sort of get your intermediate distances out to, I don't really know, a few, say 1,000 or even a few million light years. But then if you want to go to billions of light years, you really need these exploding stars. Certain massive white dwarfs, if they get pushed over the limit, the Chandrasekhar limit, they'll explode and they'll blow up and they won't leave anything behind. There's no supernova remnant. but that we think we know exactly how much energy that is, so we call these sort of standard candles. And so this was sort of the key project for Hubble, as I was saying. And then, now the key project for W first, well, Nancy Romain, will be to look for more of these Type 1a supernova. And so Alex Filipenko had a dedicated telescope in San Jose, and then Schmidt and Perlmutter, they didn't use really large telescopes, but the trick is to observe as many Type 1a supernova as you can, and they may find 100 a year, right? There's sort of one per galaxy per century. So, and of course, fortunately, there's at least sort of, I think, 3 trillion galaxies now, or 300 billion galaxies. So there's lots of stars out there that may explode, but Type 1a supernova are still kind of rare. The death of a star in a supernova is, and this is where stellar evolution, we've had both the pulsating stars, the red giants, and let me see let's see if I have this one picture. Yeah, so this is what stellar astronomers love, this Hertzsprung-Russell diagram where you plot the brightnesses of stars as a function of temperature. And we cheat a little bit, and we go from the left, the hot stars, over to the cool stars, and the faint stars up to the bright stars. And so then as stars leave this sort of our sun is on the main sequence now. It's sort of an adult star is going to burn hydrogen to helium in its core and live for billions of years on the main sequence. But then as it leaves the main sequence, it can go through these pulsation. This is called the instability strip. And so the Cepheids can have long periods and be about 10,000 times brighter than our sun. And the RR Lyras can pulsate about 1 to 3 days and be about 10 to 100 times brighter. And so if you measure those periods, which of course you can do with a nice space telescope, because if you're on the ground, it could be rainy, it could be cloudy, you can't really get the periods as accurately as you can. And so, that was, like I said, so that was the key for one of the key projects for the Hubble Space Telescope. So, and I wanted to mention, where is he here? Our boy Hubble had help from Milton Humanson, who was actually helped transport things up to Mount Wilson, and then he stayed on as a really skilled observer. But of course, they didn't call it the Hubble and Humanson telescope, did they? They call it the Hubble. But anyway. So Hubble was trying to figure out whether these collections of stars were nearby. People didn't really understand how big the universe was. The Andromeda Galaxy, which some people called a nebula, they didn't realize it was 2 million light years away. They thought it was inside our own galaxy, the Milky Way. And so in trying to figure out how far away galaxies were, Hubble, as he measured these spectra, where's our spectrum? Here's our spectrum. So if he took a spectrum of something in Virgo, our favorite little violet lines were slightly shifted towards the blue. And then as we got to 1 billion light years, 1 gigalight years in Coma Borealis, those purple lines are showing up in the spectrum. And so you can think of this as like a prism. We're dispersing the light from the galaxy across the prism, that we can see the individual colors, from violet through yellow all the way to red. And then what he found is the furthest galaxies where we had the biggest redshifts, those violet lines are now showing up in the red. So instead of at 390 nanometers, they're at 700 nanometers. And this was a real surprise. And I don't think Hubble really, they didn't sort of, he tried to measure Hubble's constant, but like I said, his distance indicators weren't very good. But then it was George Gamow in the 40s and 50s who sort of worked out this idea that the fact that all the galaxies are moving away from each other, if you run the film backwards, where's my other little picture? Here it is. So today the galaxies are here, but some earlier time they were closer together. And if you run the film backwards, then there must have been the need for a big bang where everything was sort of infinitely hot and infinitely dense. And I guess Fred Hoyle was giving in a radio interview, sort of putting down the Gamow theory, and he called it the Big Bang, and that name kind of stuck. So,
right.
Yeah.
So you talked about the Type 1a with the what was the word you used?
The accreting white dwarfs, or
yes, accreting white dwarfs. Is there any other type of star that can give us information? I mean, or is it just those accreting white dwarfs?
No, we use some of the brightest, the most luminous O and B stars that can be, they can be 1 million times brighter than our sun, and they can be about up to 100 times the mass of our sun. And so we like to look for those in distant galaxies. And there was, let me see here, these. There's a group of stars called the tip of the red giant branch. So those ones in the Hubble diagram that are some of the biggest and brightest stars, like Betelgeuse, is maybe 500 times bigger than our sun, probably 1 million times brighter, but don't quote me. It's cool, and so we can measure some of those what they call the tip of the red giant branch stars, and so it's kind of a nice sort of there's sort of this competition, right, between stellar astronomers and cosmologists a little bit, right? And so now there's sort of this synergy that understanding how stars evolve off the main sequence, how they die and go through their life cycle is really an important piece of information then to measure these distances and sort of set up the playing field to understand the size and distance of the universe. So I always thought that was kind of cool that you kind of, even if you're trying to study galaxies, you have to kind of come back to stellar evolution. And of course, our Milky Way has about 200 billion stars, and there's probably, I think, I forget the some of the James Webb results are saying there's about 3 times more galaxies than we expected. So I forget what that number is. If it's, I think it might be 3 trillion, up to 3 trillion galaxies now. So
wow,
a lot of
it's
galaxies.
mind-boggling.
Yeah.
So
But
this probably is well, there's no such thing as a stupid question, but um, what is the difference between a neutron star and a white dwarf?
yeah, so our sun will become a white dwarf. That's where once our sun runs out of hydrogen, the helium, it'll be hot enough to fuse up to carbon, and then gravity will squeeze the white dwarf down to the size of the Earth. So a white dwarf is about the size of the Earth. Whereas now, if that's in a more massive star, it can fuse that carbon into heavier elements like oxygen, neon, magnesium. But then when you get to iron, Frank Hsu called iron the ultimate slag heap in the universe. You start slamming iron nuclei together, they don't give you, fusion is done, you don't get any energy back, and the core collapses. And so if you squeeze a white dwarf down to the size of a city, so a neutron star has a diameter of about 20 kilometers. And so you can think about it, you're taking all the free protons and electrons and squeezing them together, and you're making a neutron soup. And so this has an atomic density. It's going to have a density of 10 to the 12 times that of water, or some 10 to the 11 times. It's going to be incredibly dense. And we discovered them in the 60s as pulsars, as spinning stars. And so that neutron stars, it's sort of the next step up in stellar evolution from our sun-like garden variety stars that make white dwarfs. So you need more mass and more fusion, more gravitational potential energy then to have a stellar corpse, a compact, or what's left after the star's life. And a supernova can go off and leave behind the neutron star. It may destroy it. And then if that neutron star is over 3 solar masses, then there's no known force in the universe that can stop it collapsing into a black hole. And so basically, a stellar mass black hole is just a neutron star now that its escape velocity is so high that not even light can escape. So, and then when we think of it as being a singularity, but that's also a hard concept. So yeah, so
I gotcha.
So the most massive, like sometimes you'll see in the news that our sun will blow up in a supernova. It never will. It doesn't have enough mass. It will stop at making carbon, basically, maybe some oxygen, and it'll fade away. The outer part will expand into a red giant, crispify the Earth, and then the core, the inner 60% of the sun, will die as a white dwarf. And white dwarfs are neat because they form at about 100,000 degrees, and then they just cool off like a brick out of the oven for billions of years. And there was always an idea to try to find the hottest white dwarfs, and of course, those are going to be ones that formed more recently. But they tell us sort of a lower limit to the age of the universe, because there was back in the 90s when people believed the universe was only 10 billion years old, there was a group of astronomers measuring a high Hubble's constant says the universe is only 10 billion years old. But we knew of white dwarfs that were 12 or 13 billion years old that have been cooling for a long time. And so, now I think everything works well with a 13.7 billion year old universe, because our 13 billion year old globular clusters and our 12 or 13 billion year old white dwarfs can exist. We don't have this sort of paradox, but so yeah.
I have oh my goodness, so many questions. But I want to get to two more of the questions from our live chat because I'm sorry.
That's great. Yeah.
All right, and we are getting close to the end of our show, and I can't believe it. It seems like we just started. It
Yeah,
really does feel like we just started. So I have so much more to ask. So Wes asks, in what ways can you determine how old the universe is? Does microwave radiation tell us this?
Well, I mean, that's a good question. I don't know off the top of my head, but I think in the certain Big Bang model that we think of the universe as having cooled from when it was radiation dominated after about 400,000 years, and that at a temperature of 3,000 Kelvin. And so if we measure the temperature today, then yes, we can sort of tell the age. If it was 10 degrees Kelvin, the microwave background now, then obviously the universe would be younger. If it was even cooler than 2.7 Kelvin, it would probably be older. So yeah, the temperature does sort of naively tell us the age of the universe. I guess the one way is the Hubble's constant is kind of like 1 over the age of the universe. And so if we measure a certain Hubble's constant, the galaxy distances give us a Hubble's constant about 73 kilometers per second per megaparsec, and that turns out to an age of about 13.7 billion years. And the error bar is kind of small, but then of course the cosmic microwave background is saying that it's a little bit young. I think it's small, a little bit older. It's getting 67 kilometers per second per megaparsec. Then that might give us an age of 15 billion or something. But I think, as a stellar astronomer, I sort of err on the side of what we get from the galaxies, but we'll see. I think this is an area where James Webb will help a lot. And then, like I said, when they launch WFIRST and now the Nancy Romain telescope, we'll see. But yeah, that's a great question. It's, you can see sometimes at talks, cosmologists will show the age of the universe as a function of time. And then the last 50 years, it's changed quite a bit. We went from, some groups believed in the 80s and 90s it was 20 billion years old or 10 billion years old, and now we've kind of converged on this almost 14 billion year old age, which I'm happy with. But we'll see. It's subject to newer information.
So, you said the Nancy. What was the last name?
Nancy Romain. I think she was a NASA administrator or something. But yeah, and I can't keep track of some of these new missions because they name them after people, and then you knew the acronym. But it was called WFIRST. It's sort of the next big flagship NASA mission, and its main goal is to look for Type 1a supernova.
That's going to be exciting.
Yes,
very exciting. Is there any estimate for when they might actually launch?
Let me Google it.
Oh, we just love Professor Google, don't we?
Yes, it says 2027.
Okay. Yeah. So not too far off. That's good.
No, but it's coming quick, and hopefully it doesn't have the delays that our lovely James Webb had. But
right.
I'm 2027 might be a bit optimistic. But yeah, all of these will contribute. But that's one of the things that I think it's hard to understand is that a lot goes into measuring Hubble's constant. The Earth's sun distance, and then the distance to the nearest pulsating stars, and then the distance to the nearby galaxies, and so that we build this distance ladder, and any little error as we then that ladder is longer or shorter than it's supposed to be. And yeah, I think Hubble, if I remember, his numbers were big, and so he got an age of the universe of about 2 billion years. Because his distances weren't big enough. So,
wow.
Yeah.
So Dr. Tapioca Weasel asks,
yes.
I think the equation of state is different I think for us as well. Is that
Are you meaning for neutron stars or?
I bet that's what he was talking
Yeah,
about because that
yeah,
was right whenever I was
yeah,
talking
white
about
dwarfs
that.
versus neutron stars. Yeah, yeah, if you look at sort of one of the weird things about white dwarfs is because they're under so much pressure, they're degenerate matter. They can't sort of heat and cool. They just get hotter, and that's why they're born so hot. Whereas a neutron star is going to have a very different equation of state. And there's lots of studies of, the neutron soup, that the crust is sort of a lower density than maybe the core, but there's lots of great physics. And of course, a spinning neutron star is just as good to test general relativity and things at the inner boundary. So yeah, no, that's a great point. Yeah.
So we actually have a couple more that have come in. Are you able to stay just a little bit longer?
Oh yeah, yeah. We're having
Great.
plenty of
Okay.
time.
So Begin to Know asked, what's new in solar physics? I
Well,
love that question.
yeah. Well, one of the great things is about 2 years ago we commissioned the largest solar telescope in the world in Maui on Haleakala. It's a 4 meter called the Daniel K. Inouye Solar Telescope, and it's sort of has we have a resolution of about 20 kilometers on the sun compared to 100 with all our current instruments, so about 5 times better. And so, the sun is ramping up towards solar maximum, which will happen in about 2025, although it may be earlier. But yesterday, the sun has a huge new sunspot, active region 13590 or something, and it's a ginormous sunspot, and it's had two X-class flares, and they're the biggest flares. And so we have to worry about our infrastructure. The 1859, there was a huge solar flare called the Carrington event that melted telegraph wires back in.
Wow.
And now if we had, and there was a solar flare in 1989 that knocked out power stations in Canada. And so if we had a similar event now, we have so much technology and satellites and things. And so we like to keep an eye on the sun. There's a nice web page by Trinity College called solarmonitor.org that shows it updates about once an hour images of the sun from the NASA satellite. So it's a pretty exciting time that we have the Parker probe going around the sun every 100 days, and it's going to get within about 4 million miles
Wow.
later next year. And so it has some type of heat shield, but it's going to get up to 2,500 degrees, and it's done about 19 orbits already. So that's called the Parker Solar Probe. And then the Europeans launched Solar Orbiter, and so we're going to try to measure what heats the outer atmosphere of the sun, which is millions of degrees compared to the surface, which is just 6,000 degrees. So how we heat the sun. In everyday life, things cool off, right? Your hot cup of coffee cools off, but the outer part of the sun is millions of degrees and the surface is only 6,000. So something must be giving energy from inside the sun. And there's two theories, lots of nano or micro flares or some type of magnetic waves called Alfvén waves. So
We're definitely going to have
yeah.
you
Yes, we should
back
do
for
that
a
show.
show on
Yeah.
the sun. Absolutely, because now I have all these other questions.
Mm.
Every time that we talk, it's like there's more and more and more. So there's another one from Kat the Humanist who asks, can you explain a bit for people who don't know why the universe expands, but the galaxies don't spread out?
Well, if you think of the analogy of sort of taping pennies on a balloon and you blow up the balloon, the pennies are getting further and further away from each other. So, the galaxies have 100 billion stars, and so you can think of them as kind of being solid like a coin. They're gravitationally bound to themselves, and then as the universe expands from the Big Bang, any galaxy is going to look like the center of the universe because it can look out and from some other galaxy, it looks like everybody's moving away from him, and from our galaxy, it looks like everybody's moving away from us. But then, of course, there's one complication: is that galaxies like to live in clusters, of a few hundred to thousands of galaxies, and those galaxies are gravitationally bound. So the expansion of the universe probably isn't making our clusters of galaxies bigger either, because they're kind of a unit too. But so hopefully that answered your question. As the universe sort of stretches in all directions, you can think of it as a point that's being stretched. That the galaxies are like coins on a balloon. That we don't think of them as spreading out. So
maybe the galaxies that are kind of bound together are
Yeah.
like the dollar bills. So it's like bigger.
Yes. And then came inflation. But yeah.
Yeah. Then we have Leophilius who asks, is that 2,500 Fahrenheit or 2,500 Celsius?
Oh, for the soil, the surface of the sun, we think of as physicists like to use Kelvin, so it's I guess closer to 6,000 centigrade. I mean, uh, we would let's see, so yeah, 6,000 Kelvin would be about 6,000. You add 273, right? So
We need to do some math now.
yeah, it's within. It's only, you think of it in terms of Kelvin. It's within 273 degrees. So yes,
It
we
looks
don't use
like,
Fahrenheit very often.
let me
Thank
take
you.
that one off. It looks like he says, I'm at the temperature of the Parker Solar
Oh
Probe.
yeah. Oh no, yeah,
Okay.
that's a good point. I think they think of it in terms of. Now we talk about heat shields. Yeah, we're measuring centigrade, so it's pretty hot, hotter than a pizza oven. And it's done. There was some worry NASA. They didn't really know how long it would last because as it gets closer and closer to the sun every time, um, it'll get hotter and get hit with particles and things. But knock on wood, it's been working very well. The one sort of design issue, the Parker probe doesn't have an imager. It's only measuring velocities and magnetic fields and things and plasma density. So solar orbiter does have an imager, but so we try to combine. When the probe goes close to the sun, we try to take ground-based observations so we can see what's going on. And also, there's the Solar Dynamic Observatory. So, yeah, thanks for that question. Yeah, it's hot. I think some engineers were probably freaking out when they were told they needed to design something to handle.
Well,
5G.
Leophilius, you need to keep watching so that you can check out we're going to have us a sun show. We're
Yeah,
going
that
to
would
have
be
us a
great.
sun
Yeah.
show. We have to do that. So I want to first of all thank all of the great questions from the live chat. We have a great live chat every single week. I'm just amazed at the wonderful questions that they come up with, no matter who the guest is. But I really want to thank you, Damian, for coming on and sharing all of your great knowledge. And it really doesn't even feel like we've gotten started. It feels like,
Yeah, well,
you
there's
know,
the universe. It's a big topic, right? There's so many different pieces, and yeah.
absolutely. Do you have any final thoughts for our viewers?
Yeah, I think that the Big Bang is a theory. It's not the law of the Big Bang, and I think we're going to keep adding information to it. And I think sort of the headlines that say it's broken are disingenuous because as James Webb and other missions and studies show new pieces of information, we kind of fold that into them and we just keep improving it. So thank you. Yeah. So it's exciting. I always tell my students that dark energy is 70% of the universe and we don't know what it is, but it's like job security.
Yeah,
We're gonna go.
absolutely.
We have the scientific method, and we're gonna go figure it out. And it is funny. I was at that meeting in 1999 at Fermilab where their cosmologists were like, "Well, it's done." And then, of course, we discovered the accelerating universe. So I guess life is surprising. So the universe is
Yes, it
surprising.
is.
Thank you,
And that's
Sunny. It's been great seeing you.
absolutely, that's what makes science so awesome and so
Yeah.
exciting. I think to me is that it's like a never ending big bowl of knowledge just waiting for us to chomp on.
Yeah.
And just when you think you're full, you get more. So
Yeah.
it's just awesome. It's just so great. So,
Manja, manja.
there's all different kinds of stuff, part of that soup that you can chew on too. So it's awesome.
Right.
If you like what you have seen, if you like these types of guests and types of shows, keep in mind that you can help us out and you can help us to see us more. You can like, subscribe, hit the bell, all those good things that you hear on every YouTube channel. But there's another way you could help us if you want to. We are in the process of becoming a 501c3, and that takes money. So think about maybe becoming a patron. I want to thank our current patrons, Eric Ozols, Rion, Deneen Murphy, Dan D, Michael Wiseman, Kathy Cotton, Cindy Plaza, myself, Aaron Coalson, Phil Calderone, Amanda McLeod, and Logan Fisher. We want to thank you guys so much. You help us do all that we do. I also want to remind you that we have so many other great shows. On Saturdays, we have The Global Atheist, which comes on, and then right after that is the Women's Atheist Unload. And then my little list went bye-bye. Just all of a sudden went bye-bye. Okay, let me grab my little list over here. Because we have, on Thursdays, we have my show. Oh, where did my list go? Wes, pop that list up of all of our different shows because I don't want to miss anything. Let's see where
it was last week's show. They don't have a new one up.
Okay, all right, thank you. That's why you must have gone bye-bye, huh? Check out all of our other cool shows. And don't forget on Sundays, we have Let's Talk where you can call in and talk to our guests and talk to our host. So we have Secular Soapbox. We have all kinds of great shows. So if you want to see something, it's something, there's almost something for everyone. So check us out. In the meantime, remember to always think critically. Good night, everybody.
Part of our being knows this is where we came from. We long to return. And we can, because the cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself. If we are not able to ask skeptical questions, to interrogate those who tell us that something is true, to be skeptical of those in authority, then we're